right, so we're recording, and I'm gonna start off with the I/O part. So I had worked on this a little bit yesterday, so we're just gonna kind of go through a few things. It's not a bad unit at all, and there were only like 8 questions that we had to really kind of deal with. So, like, yeah, it's really nothing too crazy. So when we have, here's the, okay. So when we talk about input output, right? Right? We know that in this case, we have dealt with processors, we've dealt with memory management. Now we're dealing with the third, or technically second main component, which is just going to be our input output. So we know we can get things from keyboards, from the screen, from the disk. We all know, we use input output all the time. So we know also that we have this bus called the PCI Express bus, right? And this essentially kind of connects everything. It's also called the, I think like the membus as well in some places. Sorry, not the membus, the IO bus as well. PCI Express is like the better way of kind of putting it. Like it's more of like literally an express bus. So you could think of it as being a little bit faster and essentially connects all of our input output devices. So like our network interface card, that's the NIC, any solid state drives, right? These is a driver. And it connects it with our memory uh, and allows us to process it from there. So that's what we have the IO/PCI bus for. So this diagram is quite important. This is showing, right, kind of the different parts of how we interact with a user program. So kind of as I said before, we dealt with process management, right? That's like threads, pthread, create, all that kind of stuff. We also dealt with memory management when we had in the unit that we were talking about. Well, actually, no, we're going to talk about that today. More like with paging, in the sense of how do we kind of find ways to store memory efficiently and to receive that memory efficiently, right? We do this with paging. So paging is like the main way of dealing with this, because we want to make sure that we get things in fixed size pages and fixed sized frames. But this is dealing with the IO part of this. So this is, sometimes they say it's the third part. Also, sometimes Akinlar puts the two of these guys together. So it's just one of the main components that the OS deals with. So inside of the IO subsystem, chances are this is probably going to be something that he might talk about, right? There are two main components. There's the device-independent software layer and the device-dependent drivers. So the device-independent layer is like the software layer, right? This is what deals with your system call APIs, and this is what's essentially kind of dealing with the actual code itself that tells it how to kind of like communicate. The issue is it doesn't know how to communicate with specific hardware. This is where the device dependent part comes in, the drivers. Think about like if you have a printer or a mouse or really anything, you have to set it up by installing a driver. A driver is essentially the translator that allows you to translate from the hardware itself to the code itself, right? That's why it's like the middleman over here. So these are the main components within the IO subsystem. Okay. Another thing is with the drivers, right? Now we're getting more into like the drivers. So this is kind of the once again, the translator. It's composed into 3 main components, and this is actually going to be one of the questions we'll get to as well. Think about how many like possible devices there are in the world, right? There's so many. I can't just say, oh, I'm going to have like 15 Apple device drivers and 20 for Windows, and there would be an infinite number of classifications. So we are kind of making it a little bit easier by putting it into 3 places: character devices, block devices, and network devices. So these are pretty self-explanatory. Character is whatever gives you a character, right? Or we could think of what's called a byte stream. So the best way of thinking of it is when you think a character, you're probably thinking, oh, keyboard, right? You're typing and you're getting keys. You're typing on the keys and it's putting input onto your screen. Like if I typed in hello, right, I'm actually putting in input. And this is passing through the I/O bus, right, the PCI Express, in the form of character bytes. And we know that it accepts a stream of characters, right? And it doesn't care about block structure or storing these or doing any of that sort, right? The order that I type something in, like if I type in hello, right? It's just based on that order, right? We know that H goes in, then the E, then the L, then the L, then the O. It's not just putting in random characters, it's doing it in the order because it's quite literally almost like, kind of going back to pipes, imagine you're piping in things all in one stream. So that's character devices. Another key thing to remember is that these are not addressable and do not have a seek operation. What that's saying is when you have addressable space, right, you're able to access it like a file system. When you have characters like this, these are just individual characters. Yes, it's part of a bigger file, but they're not necessarily their own address. So I can't just say, oh, give me the character at this position, right? We're not doing a Python or C++ over here. So it's not really like a file like that. So with characters, just remember, it's a stream, a byte stream of characters. And you could think of keyboards, printers, mice, all those kinds of things. In fact, actually, if you're setting up your computer, I know on Windows it has this, but you're able to kind of connect different drivers, right? And it actually does this division itself. I'm on a Mac, so I don't really know how it works on that, but if I was on my PC, right, it actually would say, what type of device are you setting up? And it would say mice, keyboard, printer as one category, right? Because these are character devices. They'd have hard drives as a second category because hard drives and disks are the second category of block devices. And this makes sense, right? A block is just a fixed size, addressable place that we can store things. Think of like a secondary drive that you have on your computer. You can easily access things because it's addressed. I know exactly, like if I stored a file there, I could easily access it again. It's stored in fixed size blocks, right? So if it's, I don't know, like a 10 gigabyte disk, I know that like in, I don't know, like in the 500, from 0 to 500 megabytes, maybe I have one video. And then from 500 megabytes to 1 gigabyte, I have like another video. These have their own address, and it's possible to read and write each block independently from each other, meaning I can read and write freely, right? It's not like with before with the byte stream where everything is kind of like on its own and I'm just sending in a stream of characters. Here I'm actually doing reads and writes. The last category is network devices. So this is network interface cards, which are like Ethernet cards or Wi-Fi adapters. They allow for connection. They allow you to transmit what's called packets. Packets are TCP and IP, right? We know TCP, if you took 355, which was the internet networking class, I believe. I think Justin was doing a project for that earlier, right? We know transfer control protocol. We know IP address. And these allow us to send and receive internet packets. That's what they're meant to do, and that's what our network devices allow us to do, right? We know we need Wi-Fi in order to really do that. So that's kind of what we're doing in this case. And these are the three main components. So next we have, so the way the drivers are named, there was a question on this. I would just literally just know that Unix and Linux have it in a dev folder, right? So kind of like this. If you're on a Windows device, it's going to look kind of like this, like a C drive or a D drive. When I was little, I used to think that it was just like a sad face. Like, why is this such a sad folder? Why is this such a happy folder? Hopefully it's a smiley face after this exam and not a sad face. So just honestly, Windows has a C or a D drive, and Linux has a dev folder. And that leaves us to the next part, which now deals with more of the software layer, right? So this was kind of more of like the device itself, right, and the drivers. Now we get into the actual I/O call itself. So there's three types of I/O calls. There is blocking, aka synchronous, non-blocking, and asynchronous. So blocking is more of like the easiest way of doing it, right? It just quite literally blocks until it gets its I/O, right? And I was kind of going over this yesterday, and I kind of had like a bit of an analogy with this. You could think of, let's say you're ordering a pizza from Gino's or something, right? When you do a blocking call, right, it's as if you order pizza and you hang up and you sit there and wait for your pizza. You don't do anything else. You don't do anything productive. You just wait for your pizza. And that's literally what you're doing here. Your process is completely suspended until the I/O is completed. So this makes it super easy to maintain, right? You just, okay, I'm waiting, just waiting. But it's also a big waste, especially in like single threaded. Sorry, I'm thinking 343. Single threaded programs, right? There was a question we had done a little bit earlier with spin locks, right? Spin locks are kind of the same thing, where it's spinning, it's busy waiting, and it's seeing, is it ready yet? No. Is it ready yet? No. Is it ready yet? Yes. Now I take it. You're doing the same thing kind of here. Is the I/O ready yet? No. Is it ready now? No. Once it's ready, then I get it. So single thread, big waste. Multi-thread environment, now you're talking. So that's something to keep in mind. Non-blocking I/O calls. Now this is involving, right, setting what's called the O non-block flag, right? This is kind of like the flag that when you declare the I/O call itself, you would just kind of write this down, and this lets you enforce what's non-blocking. And what this does is it kind of does like a half-assed job. It returns what it can. Here's what I got. And then it goes back and it does it in the background a bit. So it's going to return immediately with the count of bytes written, and you're going to be able to kind of wait upon that a little bit more, but you're not necessarily blocked at that point. So you can kind of still go, but you have to just kind of keep track of, okay, am I still getting the data yet? Or, is the data ready yet? So you're still going to wait. And the analogy for this one would be, let's say you call up for your pizza, and, they're kind of busy at this point, right? And they say, okay, well, I'm sorry, I only have your garlic knots at this point. You take your garlic knots and you eat your garlic knots, right? You have whatever they've returned at this point. And while you have your garlic knots, right, you're doing some stuff, maybe you're doing some work, and you call up again, is my pizza ready? And they're like, sorry about that, still no. So you continue. Again, you're not blocked. You're not just sitting there doing absolutely nothing. You're doing something. You're eating your garlic knots. So now you finally call up and it's ready, and now you can get it. So that's when we have non-blocking. So this is a little bit better when you have a single threaded environment, because you're able to kind of actually have this like kind of work a little bit more. And right, this is more important when you want things to like actually have good response time to it, right? So event-driven programming, this stuff you really want to make sure that it is, working. You could think of it as, if you really need something like responding very quick, you don't want it to just be waiting. Or if you're really hungry, you need at least some garlic knots, even if your pizza's not ready completely. Okay, and then the last part is the asynchronous call, right? This one is more complicated, so it's only really used in like higher end programs. But this is quite literally the process runs completely while the IO executes in the background. So this is not doing really a half-fast job like the previous one. It is literally doing everything it wants in the background while the IO is being fetched. So in the case of like the pizza example, you call them up, right? You do a callback, and they say they're going to call you back. Literally, that's what callback means. We'll call you back when it's ready. And let's say they give you like a pager or a buzzer or something, and they'll say, "Okay, we'll call you when you're ready. Go do something." And you go and you go to the mall in the background, or you go shopping. There's a store next door to Gino's that just opened, or something like that. Um, so you do all these things while it's there. You never check to see if your pizza's ready again, because they're the ones that are going to call back. So it's a little bit more higher end than the non-blocking IO call, because you're not responsible for the waiting itself. This is why it can be difficult to use and implement. So the types, the use cases, right? We know blocking, very simple cases, especially when waiting is acceptable. We want to try to avoid it with the single thread environments because it can be very wasteful. Non-blocking is better for things that need a little bit more oomph to them, right? Something that needs better response time. Event-driven programming, network servers. So again, network servers, you want them to be fast. You want to be able to have high response time. So that's why we want to have non-blocking for that. Also, it's good for single-threaded applications because you want to be able to multitask a little bit. Asynchronous would be nice, but this is more for high-performance applications because of how complicated it can be. You want to make sure, because this is great when you have a lot of overlapping I/O to it, because this allows you to quite literally, truly multitask. So that's the difference between the three of them. Okay. And now continuing with device independent software layer. So what else does the device independent software layer do? A reminder, right? If we're looking at our program here, right? We've done the device dependent part. These are the drivers themselves. We went through a little bit of how the IO calls happen, right? So we know how to do that. Now we're looking at what else does the device independent software layer do? And it does a couple of things, right? It does scheduling, so figuring out, with IO requests. If something is waiting, it's waiting on a queue, right? Its own IO queue. If it's waiting on like a keyboard, it's waiting for the keyboard. So it's on its own waiting line. Also buffering. So this is storing data in memory while transferring between devices. So in order to make sure that, you can't have all of your, you can't have necessarily all of the data kind of immediately going into the memory. You have to kind of do it in chunks, in buffers. So this lets a little bit go, then gets another buffer. Gets a little bit go, and continues. So in this case, right, if you have network packets arriving, your application writes 10 bytes at a time, right? And the disk write size is 1 block. So I don't want to write like every single byte. Like if there's like 100 bytes, you can't write that all at once. You take little bytes, literally little bytes, and that's what allows you to do this buffering. So just take little bytes at a time. And caching, we know caching very well. That's being able to retrieve the data pretty fast from a very quick storage system, right? And it's just kind of holding a copy of the data for us that we can get very quickly. And this allows us to have very good performance, right? We can keep frequently used items in this cache. And, depending on the cache principle that we use, maybe it's first in, first out, or least recently used, whatever it is. We're essentially trying to get things from the cache as much as possible. And that's about it. So this diagram is pretty much a recap of everything that kind of happened before. So honestly, if you can kind of think, like, go over, if you understand this, this is pretty much like everything that's kind of going on here, right? We know we have the user process itself, that's the code, and that's what makes the request, right? It makes, like, say, recall. This is actually the first question of the question set too. So we know the user process is what makes the call itself. So if it's a read, a write, whatever it is. And this is going to now, make the IO call, trap to the kernel. And the kernel is going to handle the device independent software layer, right? This is what does all of the things that we had before. The scheduling, the buffering, the caching, and keeping track of the states of processes, all of that fun stuff. This is also what is handling our blocking, right? So those are the blocking calls that we talked about. After that, we're able to communicate with the hardware using the driver. So this is what's going to translate this IO code that we have, like the read, call, whatever, to the hardware's level. And we're able to use a hardware interrupt, right, to get into the hardware itself. Because we have to interrupt to say, hey, we have we need to have the IO. We need to have, if it's a keyboard, we need to wait for the input on the keyboard or on the mouse or etc. So we have our interrupt handler to handle that, and we're able to wait on the hardware who actually performs the IO operation. And we waterfall down, and that waterfalls back up again. So that kind of does it in reverse and allows the user process to receive the input that we requested. So this is kind of just a more detailed version of the one that we had before, right? Sometimes there's another layer for user level IO. This is just kind of like a system call library in the sense that it kind of allows you to format things nicely. It can help you with if there's buffering with data. It's just a bunch of performance stuff. So it's nothing too crazy. But this is pretty much the gist of input-output. So going to the questions now, right? We did this one. What is a device driver? Why is it necessary to implement a new device driver for each OS, right? We kind of said before that it serves as a translation tool between the device independent software, right? And the user process itself, and the hardware, because the hardware is very specific, right? We can't necessarily make code for every single device. That's what the driver's for. The driver is what handles that. So every OS has its own APIs, right? And we use these drivers to interact correctly. So you want to make sure you have the driver that can translate specifically to that OS's environment, right? This allows your printer to connect to your computer. And sometimes you need a different driver, right, for maybe Mac OS versus Windows. And that's usually why they'll kind of ask, hey, what OS are you running before you download a client? Because this is exactly why you want to make sure you're translating between the right languages. If you're translating between let's say English and Spanish, and your OS is running Italian, that's gonna be a problem. So that's what our drivers are doing. Okay, briefly explain how Linux classifies all I/O devices. Give one example of an I/O device under each category. So these are the 3 categories we had mentioned before. So we have characters, we have block, and we have network, right? So character, it's anything that's giving you a character at a time. So printers, keyboard, mice, basically anything that's a byte stream of characters, right? Quite literally, think character, think like you are typing on your keyboard. Block, think of whatever is stored within blocks. Think of a hard drive or a disk. And we know that these are always going to be in fixed size address blocks. All right, that's what the word block is for. Then lastly, we have the network devices. These are our network interface cards. So we have Ethernet cards, Wi-Fi, anything that gives you like a signal and can transfer different packets, right? So that is for that. The next part is, how does Linux name I/O devices? Is it different than Windows? If so, how? So this is just simply Linux has the dev folder, Windows has the D and C drives, right? Briefly explain the I/O call semantics available in Linux. If you have a single thread application but multiple file descriptors to read from, which I/O call semantic makes more sense? Would your answer change if you have a multi-threaded application? So these were the three that we went over before, right? So that is the blocking, aka synchronous, non-blocking, and asynchronous. So we know that with blocking, right, the entire process stops. So this is not good for single-threaded application. So if you had a single thread application but multiple file descriptors to read from, right, that's telling you have a lot of I/O to do. Do you really want to be blocking for every single I/O? Probably not. So if you had that, you probably would want to use non-blocking, just because it's a little bit simpler to use than asynchronous. I mean, asynchronous is nice too, but the non-blocking would probably make more sense because it's a little bit easier to use and would allow you to multitask a little bit more. Would your answer change if you had a multi-threaded application? So this would change because with a multi-threaded application, right, I can block. There's nothing wrong with having a blocking I/O call, right? Blocking I/O, all it does is, it's bad if I have only one CPU and it has to wait on that. But if I have multiple CPUs or multiple threads in this case, right, I can wait on one thread but continue on another thread. So in that case, keep it simple and straightforward, right? You want to make sure that you use the simplest one, and that would actually be the blocking. I mean, if you wanted something high performance, well, this doesn't say anything about performance wise. So, like, you don't have to say, like, oh, I'm going to go for the best and the biggest, like the asynchronous one. But I don't think there's necessarily like a perfect answer for that. I think as long as your reasoning is correct. So for this, I would personally say, right, you want to do non-blocking for the single thread, right? It's a little bit easier than the asynchronous, and you wouldn't be getting stuck with the blocking. And for multi-thread, you'd want to just have a simple blocking. Makes it a little bit easier. You could also do asynchronous. Honestly, any of these could work, but probably blocking, keeping it simple, sometimes that's the best solution. Okay, so list 4 functions of the device-independent software layer. So this is the part that's handling, right, a lot of the background stuff. So like scheduling between processes, buffering, caching, and also kind of keeping track of what process state you're in, right? So like, do you have an open file? Are you connected to a network? All that kind of stuff. Trying to come up with like an acronym to kind of remember it. It's like SBCPS, something like that. It's not really helping me right now, but if I come up with an acronym, I'll let you guys know. But just the main thing, when we hear device independent software layer, this is like the behind the scenes stuff, kind of handling like a lot of the kind of, I guess you could think of like like office work in a sense. It's like scheduling the different threads together in the I/O requests, handling what comes into the actual memory with buffering, caching what gets saved, etc. So that's kind of what's going on there. And lastly, I think, yeah, for this part, given that the OS already provides read and write system calls to read from and write to an I/O device, why do most programmers still prefer using a high-level I/O library to perform I/O? So we kind of went over this a little briefly in the sense that we have sometimes over here, right, between the user program and the device independent software layer, we might have a user level library. And this is mostly handled for just performance reasons, right? Whether we want it to be formatted nicely or handle the buffer a little bit differently. These are a library of function calls that allow us to um, have a little bit of better performance in our code and for our I/O. So that's really the main reason, right? In the PowerPoint, he gave the two main ideas of formatting and buffering. So in general, it's just kind of just some extra that allows us to have a little bit smoother code. I mean, it's as if you're using like an API in your own code, you know? Like you don't need it, but it's like you have like kind of a library of functions that are already kind of pre-made that kind of make your life easier and can kind of help your performance and formatting of things. So kind of the same thing. So this is the end of the input output layer. Did I miss anything, Justin or anybody else?
Just the I mean, there's still also the disk stuff that I told you about. Um, that's from topic 9, I believe. That's the device parameters, I think it's called, or something.
Yeah, I gotcha. So we can go over quickly the secondary storage. So I haven't gone over it as much right now, so I've just mostly been going over that a little bit today. But when we talk about secondary storage, right, this is kind of like our hard drive on our computer, right? It's kind of separate from like the RAM itself. So we're not really having like pure access to it, like fast access to it. I mean, that's what I mean. So because of that, it takes a little bit longer. So instead of dealing with like the IO bus, right, which is what we kind of dealt with before, we're going to be dealing with the mem bus, right, the memory bus, also called the front side bus. So he likes to call it the front side bus. I kind of looked it up. It's the same thing as the mem bus. So if you remember a little bit from computer architecture, the mem bus or front side bus takes a while, right? Because we're literally going from two different pieces of hardware, right? We're attaching our secondary storage to our RAM, which is like our primary storage. So because of that, it takes a little bit longer. And this is why we want to try to avoid like going deep into memory as much as possible, right? As much as we can with frequently used pieces of memory, we want to try to put it in our RAM or even better, our cache as much as possible, right? Cache is like the fastest, right? It's right on the CPU. RAM is like okay, but the secondary storage is like really slow because think about it, you have to go over the membus, then you have to go to get onto the CPU. So it's gonna be like a lot of stuff that's going on here. So we know that secondary storage is quite big. Think of like an external hard drive, right? Maybe it's gigabytes or even a terabyte of storage. Um, Hard drives themselves can be pretty cheap, right? Especially if they are um, not necessarily solid state, right? So if it's more of like the spinning kind per se. And it tends to be quite slow. So even though milliseconds doesn't sound like that much, we talk a lot in nanoseconds. And we know that we have two variants of it, the hard disks, just your hard drive, and non volatile memory, which you might know as solid state disks. So a hard drive is what's going to kind of look more like this, right? Kind of looking almost like a CD drive. And it spins, right? You have the platters themselves, which are like the round circular things. And each of these has different tracks on them, right? So you're able to kind of essentially travel between these, right? Using this arm that is your read write head. And as this spins, it's going to pick up the data within these different pieces, right? So the cylinder here, you see it actually looks like a cylinder. This is kind of, you can think of like the row that we're on. So there are more cylinders per se, you know, there's different like tracks as you go outward, right? This is one track, but on this disc is more tracks. Think of like a record, right? A record might have like a dozen tracks on it or something, and wherever you place the head is where it's playing the music. In this case, wherever you're putting the head is where you're reading or writing from this. Each of these tracks has the sector, which is just a little piece, right? And what we want to do is essentially try to minimize the amount of movement, which is the main goal of disk scheduling. This we are not going over, so literally we only need to really know these first 6 slides, and probably not even that much. So don't even worry about any of this. The main goal.
From what he
Yep.
told me, if you go up, it's that one right there, disk performance one. It's mainly knowing about the seek, rotation, transfer stuff.
Gotcha. Okay, so really this is the key. Okay. Yeah, so the main thing that we want to keep in mind with disk performance, we have seek, rotation, and transfer. So seek is moving the disk arm to the correct cylinder. So this is saying, right, you know how this is a cylinder over here. There is also a cylinder, there's more than just that one cylinder, right? I can go more outward and have another cylinder. You could think of it almost like if you had like a record, right? You're playing the different tracks. If you move the head a little outward, right, you'd be part of another cylinder in this case. So our seek time is moving the disk arm to this correct cylinder, right? So it also depends on how fast this arm is able to move, right? It's a physical component. There's going to be limitations. So some can move a little faster, some cannot move as fast, but you're dealing with milliseconds, which again is not as fast as nanoseconds. Average seek time measured or calculated based on 1/3 of tracks. I'm not really sure what that's referring to. Unless it's kind of saying how there's 3 tracks here, right? There's 3 of these platters, so you're kind of able to read these 3 at the same time, per se. I think that's what it's referring to. Justin, can you confirm?
Sorry, can you repeat that?
For this part, average seek time measured or calculated based on 1/3 of the tracks. Is that because like there's the 3 here and you're kind of reading these 3 at the same time?
I don't think so because I'm pretty sure that there isn't only one. I think surfaces, platter. I don't think there's only 3 platters in every like hard drive or disk. I think I would assume there's more than 3. But I'm not entirely sure because I didn't review this section yet.
Right. Alright, when in doubt, AI it out. So a cylinder is a set of tracks across all platters that are equidistant from the center. So, right, we know we can kind of draw out a literal cylinder in a sense. So that's kind of how we're defining that. And yeah, I'm not honestly too sure about this. It seems to be more of an approximation, honestly. Um, yeah, okay, I guess it's the accepted
Yeah,
way of
I'm
it.
not entirely sure, but I think if you were to ask this, it'd only be like one sub question, so it isn't really that many points, honestly.
Yeah, I think just honestly just kind of like thinking like of that. Um, yeah, I guess so. I'm gonna just kind of go with the fact that in this case, you're kind of reading those three things at once. I know it probably would be different for every like car drive, but so we also have the rotation, right? So that's waiting for the sector to rotate under the head. So the sector itself is rotating too. Think of a CD, it's spinning around and around and around and around. So you're moving the arm like back and forth, but to get to like a piece that's all the way on this side, right? The platter itself is going to have to rotate. And this is based on the rotation rate of the disc. So again, this kind of depends. Could be 60 to 250 times per second. And there can be some latency too, because again, all this is physical, it's not always going to be exactly the same time. And the last part is transfer, so transferring data from the surface into the disk controller, and from there, sending it back to the host. So this is, remember, this is reading and writing data. And in order to do that, we essentially need to kind of account for the fact that there's going to be a little bit of latency with that. It's going to take some time to transfer that. And the effective transfer rate is 100 to 200 megabytes per second. So there's always going to be like a limitation, right? You're not going to be able to transfer, like maybe like a whole gigabyte at once. Maybe some really high end disks could, but this would be kind of a limitation. So the OS is able to kind of change these guys up a little bit, right? The transfer is more of a hardware problem, right? Like there's only so much that it can get transferred at one point. But when you have the OS itself, right, it can um, kind of figure ways to make things a little bit easier to kind of find, right? And those kind of get into those disk scheduling algorithms, right? So finding ways to make it a little bit more efficient, to have less disk head movements. Um, for instance, if let's say it was the like the elevator algorithm, again, we don't have to really know this, but just as an example, right, it goes like all the way up. So all of the like requests past a certain point, and then it goes all the way down. So all the lower end requests. And this essentially allows us to have less disk movements and kind of over rules the limitations that we have here. So the main things to remember is we have the seek. Seek deals with the cylinder. Think seek for cylinder. The rotation is for the actual platter itself. You could think of that looks like almost like Saturn's rings, right? Planets rotate. And the transfer is the actual transfer time. Do we need to know this, Justin?
Sorry, he just told me that it would just be the parameters of the disk. That I don't know what that means. I don't think he said that we would be asked like to calculate anything. I'm pretty sure it's just like, hey, what does this part of the disk do, or list three parts of the disk and what do they do, something like that. Like gave Seek as an example from what I remember. I don't know if anyone else from the review session or from Office Hours was here when he said it, but I remember him saying that. Yeah, that should be it though.
All
I think
right.
just up to disk performance one, yeah.
All right. So I guess if we were to try to take a look at a few of the questions for this, right? What is a cylinder as it applies to disks? So we've seen it before, right? The cylinder is like the parts that have like sectors that are kind of like equidistant from the middle, right? So it's an equal distance from the middle, and that's how we're kind of able to create that part. So you can kind of see these tracks are kind of parallel to one another. Rotational latency, right? So what is rotation? Waiting for the sector to rotate under the head. So the platter itself has to rotate. And this is going to have delays. So, because it is hardware, so you have to wait for it to kind of spin. Average latency is the max latency divided by 2, I guess. But I think the main thing, I mean, it's just briefly explained, so I think if anything, it's probably just going to be like literally just this. Like, you just want to make sure that that sector is able to rotate under the head. So you're at the right sector. Because maybe you're on the right track, but you're on the wrong sector. If this is the sector you want, this one that it's pointing to right now, and you're on the opposite side, you have to wait for it to spin around.
Yeah, I would just say just waiting for the like where what it says there, waiting for the sector to rotate under the head. But it says the latency part, so it says a delay. I would say the answer is to delay in waiting for the sector to rotate under the head, or I guess the amount of time it takes. Yeah.
Gotcha.
Number 10, I don't think we would get. Number 11, probably. Or seek time. Again, seek is moving the disk arm to the correct cylinder. So seek time would be the amount of time it takes to move the disk arm to the correct cylinder. And the rest, I don't think he would ask.
Yeah, definitely
Seek
not.
time again? Sorry.
Seek time would be the amount of time it takes to move the disk arm to the correct cylinder.
So seek for the cylinder is like the disk arm itself, right? Rotation is the platter rotating, and we wait for the sector to rotate under the head. Yeah, this is all like the algorithm stuff. I guess we don't have to answer those. That's a lot. Okay, well, that's the end of that. Any questions? I know that was kind of a lot, but if I had to kind of pinpoint what questions he would ask, I think all of this would probably be like, as Justin kind of said, like those subpart questions. So honestly, I doubt there's going to be more than one small part on like this disk performance stuff. Just literally the seek, rotation, transfer. I think that's the only thing that, or maybe like pieces of it, like what's a cylinder, what's a platter, what's the track, a sector, cylinder. I think just if you know these two slides, that's good. And then for the other
Yeah.
part, right, the input output, if you know this, like if you know this diagram can explain it, you'll be good. You want to know the three types of I/O devices and the blocking calls, and the rest is kind of what each of the components is doing, right? So if you know this, then you should be pretty good.
Okay.
Right.
Yeah, that should be pretty much on it on iOS subsystem. Me personally, I didn't have enough time to study on my own as well, so honestly, I think I'm just gonna finish paging for tonight and then leave iOS subsystem stuff for tomorrow morning to review on my own. But now we're gonna jump into iOS subsystem stuff. Again, we're gonna take a 30-minute break at some point, probably around 10 or 10:30 if we get to that time. If we end earlier, then obviously not. So let me just share my screen really quickly. All right. Can everyone see my screen?
Yep.
Okay. So again, this was our process synchronization stuff. If you missed a review yesterday, just watch the video and you'll be good. Just know, oh, I forgot to say this. In the office hours, he did say that the question that he gives can say, answer this using POSIX functions and things like that. So in that case, you wouldn't be allowed to answer, let's say, like a monitor question in Java. You would have to do it in C. Um, and so just make sure that you know how to do um, monitor stuff or binary or mutexes and semaphore stuff in C as well. Um, in in C, it's not that much different, especially since he is not very nitpicky about the syntax. Where here I'll give an example. Okay. For example, here, actually, here I'll redo this question really quickly just so you guys can know how to do it in POSIX notation. Just because I only taught it in Java, so I feel like it wouldn't be fair to expect you guys to know how to do it. So I'll do this one really quickly since it's pretty quick. So this question says, consider global variable g with initial value 0 that is manipulated by multiple threads. This part A says to implement the above monitor in Java, and part B says to do it in POSIX. He also did say that the coding question will be pulled directly from the process synchronization practice problems. So one of the coding questions is the coding question on the exam. And since he did say that it could potentially say do it in POSIX, this specific question says part B, do it in POSIX. So I believe the coding question may be this one, but that's just my thought process to it. It's pretty good guess that it may be, but anyways. So for POSIX notation, again, you don't have access to the synchronized keywords, so you have to do the locking and unlocking yourself, as well as creating the condition variables. So I'm going to create a lock. I'm going to call it mutex t mutex, and again, he isn't really too picky about it, but if you want, you could put pthread mutex initializer. Again, all this question is saying is you want to be able to add while the value global variable g is less than 5. You want to be blocked while it's equal to 5. And for subtracting, you want to be able to subtract while the global variable g is greater than 0, and you want to be able to be blocked when it's equal to 0. So to do this, we're going to want to create two condition variables. It's going to be cond t. I'm going to put can add and con t can sub. Again, this is a POSIX notation. And I'm going to put public void adder. And so our global variable, again, it starts at 0, and g is equal to 0. And I'm going to say, oh, this is kind of annoying. Let me move this down, maybe. Okay, I'll do that. There we go. Okay. So again, how monitors work, you're simply waiting to be signaled by another, or actually, you're basically blocking a thread from executing and just releasing the lock when it shouldn't be executing based on some condition. So the condition for adder is that g is greater or is equal to 5. So I'm going to say while g is equal to 5. In Java, it was the condition variable dot await, but in POSIX, it's cond wait. And then you're going to pass in the conditional variable that relates to it. So adder would be can add. I'm going to say ampersand can add, and you're going to pass in the mutex as well. So ampersand mutex. And then once you're able to add, so you've broken out of the while loop, you're going to say g plus equals 1. And then from there, you're going to also, since you've added to g, there's no way that g can be equal to 0 anymore. So you're going to signal to sub. Okay. And so to signal to sub, I don't remember the syntax. I'm pretty sure it's con signal.
Yeah, it's the same exact
Yeah, con
syntax. It's just
signal, and
signal.
then ampersand can sub. But if you notice, I did not lock our stuff. So he said that for the exam, you can straight up just use lock, and you're going to pass in the mutex. And then once you're finished, you need to remember to unlock. So unlock ampersand mutex. Okay. So this would be our adder function in POSIX. And then for the sub, again, it's same thing. I'm going to say, I think it's subtractor. Yeah. So while g is equal to 0, we're going to wait on the sub condition, and we're going to release the mutex. That's why we pass in the mutex. But then once we wake up on this condition again and we're good, we reclaim the mutex and we continue executing. So we're going to decrement to g because g is no longer equal to 0. And then we're going to signal to the adder because, what's it called? Because what this is saying, since we subtracted from g, if g was equal to 5 and we had some threads waiting on it, since we subtracted, now g is 4, so now we can add. So now we're signaling to can add, hey, you're able to execute now, and then we give out the mutex. Okay. So that's pretty much it for POSIX. Again, he's not too picky. You don't really have to keep this part, but it's not too hard to remember. And then this is all you really need to do for the condition variables as well. Why is it 0 again? Because it says a subtractor arrives and sees the value of g to be equal to 0. It waits until the value of g goes above 0. So while g is 0, you wait. Yep. Any other questions? No, we just have one coding question, yeah, like Lauren said. It's just that the coding question is guaranteed to be from the process synchronization questions we've been given. He gave me that hint. Okay. So that's one hint he gave. Trying to remember what other hints he gave. The process, the paging algorithms, that'll definitely be on it. We're gonna go over that in a bit. Actually, let's just go through it, and then once we get to the questions, we'll go over what hints he gave, I guess. Okay, so topic 7 is memory management. It has to do. Is it going to be from LeetCode questions? I don't know. He didn't say that. So memory management has to do with the loading and unloading of processes from our main memory. So the purpose is that a process needs to be loaded into main memory before it can run. And so the OS's job is to allocate enough memory to hold the process's code and data when the process is created. Also needs to be able to reclaim a process's memory when the process terminates and protect one process's memory space from modification by other processes in the system. What does this mean? If P1 is in memory and P2 is in memory, P2 should not be able to touch P1's memory. Okay. So some history on how we kind of worked with loading processes into main memory. At first, we were working with single tasking systems, where single tasking systems run a single program at a time, and the OS loads the program, runs it, and unloads it. So we didn't have to worry about main memory like overlapping with any other processes because we're only running a single program at a time. Okay, and it's an OS with one user process. But with multi-programming or multitasking, we want to be able to run multiple processes at the same time. And so to do this, we needed to keep multiple processes in memory at once to increase utilization. And so to do this, we introduce variable partitioning. Okay, or with variable partitioning, we partitioned a portion of the physical memory to be just big enough to fit a contiguous portion or a contiguous process in our main memory. So we're loading the entire process into our main memory in a contiguous address block. What I mean by contiguous, I mean the entire process is just put into memory back to back. It's not like broken up. Like it's not like a part of process 1 is over here, a part of process 1 is over here, and the rest of process 1 is over here. It's all next to each other. Okay. And so with this came some memory allocation algorithms for choosing which spots to choose in our main memory that'll best fit, or not, I don't want to say best fit, that'll best, that'll be most memory efficient for loading and unloading these processes. So we have 3 kinds. We have first fit, best fit, and worst fit. First fit simply just allocates the first hole that is big enough to fit the currently incoming process. Best fit allocates the smallest hole that is big enough But to do this, you must search the entire list. So it's not exactly efficient, like in runtime wise, but it's pretty good memory wise. And then finally, worst fit, it allocates the largest hole. And for that, it must also search the entire list. Okay. And this produces the largest leftover hole so that when a larger process comes in, they can just simply go in and grab that. Okay. So for first fit, again, it just allocates the first hole that is big enough. So here's an example. We have these incoming processes P4 and P5, which by the way, we'll definitely get this on the exam. P4 and P5. P4 is 4 kilobytes and P5 is 1 kilobyte. And so this is our main memory as these processes are coming in. The first to come in is P4, and we have 3 holes, 5 kilobytes, 10 kilobytes, and 4 kilobytes in that order from left to right. So first fit, it's just gonna fit in the first hole that is big enough. So reading from left to right, the first hole is 5 kilobytes. So we're gonna put P4 in there. And then since P4 is 4 kilobytes and the hole is 5 kilobytes, it's gonna leave behind a 1 kilobyte hole. Then when P5 comes in, again, it's looking for the first hole that is big enough. So it's gonna read from left to right. The first hole that is big enough is this 1 kilobyte hole because P5 is 1 kilobyte. And so it's going to fill that hole and there's no more holes left. And that is what our main memory looks like after these two processes are loaded in. Then for best fit, again, we're just allocating the smallest hole that is big enough. So we're using the same main memory at the beginning and the same processes coming in. We have to first read the entire list or entire main memory. So P4 comes in, we have holes 5 kilobytes, 10 kilobytes, and 4 kilobytes. Obviously, the best fit would be the hole that is 4 kilobytes. So I'm going to load in P4 into that hole. Now, let's say for example, this was 10 kilobytes instead, or sorry, 4 kilobytes instead. I'm pretty sure you can choose either one, but to me, I would just choose the one that comes first. Okay. So P4 goes in and the hole is gone. Now P5 comes in, which is 1 kilobyte, and again, we're looking for the smallest hole. The two leftover holes are 5 kilobytes and 10 kilobytes, and so P5 is going to go into the 5 kilobyte hole and fill a 1 kilobyte space, so the hole is going to have 4 kilobytes left. Then for worst fit, again, you're allocating the largest hole. So you're going to look through the entire list and find the largest hole. In this example, the largest hole right now is 10 kilobytes. So when P4 comes in, it's going to go into the 10 kilobyte hole and leave a 6 kilobyte hole behind. And then when P5 comes in, it's going to look through the entire list. We have a 5 kilobyte, 6 kilobyte, and 4 kilobyte. So it's going to fill the 6 kilobyte hole, and we're left with a 5 kilobyte hole. Okay, so any questions about these memory allocation algorithms in variable partitioning? Any questions?
Could you ask that question again?
I said, any questions about memory allocation algorithms and variable partitioning? Nope. Okay. Let me just make sure I didn't miss anything. Oh yeah, I think I might have missed the definition of variable partitioning. Variable partitioning itself, again, is just breaking the physical memory into variable size partitions. I don't think I wrote that. Yeah, I didn't write that here. But it's just breaking the physical memory into variable size partitions. And then the partition size is just big enough for the entire process to fit contiguously. Okay. All right, and then that's what we did here. So after variable partitioning was introduced, we were still working with physical addresses in the 1960s. And so CPUs use physical addresses to access memory. This was a bit troublesome with variable partitioning because the compiler assumed that the executable would be loaded at a fixed address, which was usually 0. And so the compiler generated static memory addresses for global variables and function calls based on this assumption. And if the process wasn't loaded at the expected address, then the memory references would be incorrect. Could you go over this? Maybe after we finish paging, because we already finished. We already did process synchronization. Okay, so the solution to this was to use relocation records that were generated by the compiler, which the OS used during loading. And the OS loader would adjust memory references using the relocation records to ensure correctness. Um, this made it so that the process could be put anywhere in memory, and the compiler wouldn't just assume that it's always at 0. Kind of like an offset. But they were pretty complex to use. Relocation records made loading processes slow, and they were error prone. And they're pretty unsafe because processes could overwrite each other's memory, leading to crashes and security issues. And so a fix to doing variable partitioning with physical addresses was doing variable partitioning with MMUs, which are memory management units, and logical, otherwise known as virtual addresses. Okay. So how it worked with MMUs and logical addresses was a CPU and processes started using logical virtual addresses, and they would work together to figure out where in main memory the CPU was trying to access, right? So logical addresses were independent of the location of the process in RAM, and the MMU must intercept every memory address generated by the CPU and convert the logical address into a physical address. What does this mean? So anytime a CPU would generate a local address, logical address, that logical address would be fed into the MMU, and the MMU would go ahead and spit out a physical address, which that physical address allowed the CPU to access the RAM or the main memory. Okay. And how did this do it? It did it with base and limit registers, where the base register holds the starting physical address of a process's memory space. Again, this is when the entire process was loaded contiguously. So the base register, there would be like an MMU for every process. And so the base register would store the first address for that process, and the limit register would define the size of the process's memory. For example, let's say the base address was 0, and the limit register defines that the address should only go up to address 255. Then our limit register would store 255. And then if we were to, query for something outside of that, then it wouldn't let us. So here's kind of what it looks like. Our virtual address is we have our virtual address and we have our offset that gets fed into the MMU. So you could think of this portion here as the MMU. And what it would first do is we would say, okay, is the virtual address less than the limit register? Okay. Now, wait, sorry. What's happening here? Offset is, hold on, I think I'm reading this incorrectly. Am I correct? So the offset is less than the limit. I was able to read this before, but P2's, oh, sorry, okay, yeah, sorry. It's if the limit register, so the value of the limit, or I guess that address itself, if that is less than the offset, meaning that the offset is greater than the limit, so let's say the limit's over here and the offset's over here, but the rest of the process is over here, then that is not a valid virtual address within the scope of the, I guess, the process itself. So you would get a protection fault. But if it was, then you would say, yes, you're good. So then you would add the offset to the base register. And then you would go ahead and access physical memory, right? So in this case, our base address is over here. And then you would add to the base address the offset. So let's say the offset goes over here, then you're good. And then the limit register would be like over here, right? So if the offset is less than the limit, then you're good to go, right? Okay. So what are the benefits of this? Benefits would be that processes could be loaded into any available memory location without modifying their code, right? Where you can put partition 4, you can think of partition 4 as for P4, partition 2 for P2, partition 1 for P1. It could be loaded anywhere into memory. It didn't exactly matter where, like you didn't have to say, okay, P1 has to go there and P2 has to go there, because the base registers and the limit registers were available within the MMU, so they could be put anywhere. So again, the base register would be set up accordingly, and you can move the process to a different location without any problems. How you would just change the values of the limit register and the base register. It also had memory protection, along with flexibility. It had memory protection, where the limit register prevents processes from accessing memory outside of their allocated space, providing memory protection among different processes, right? So it, let's say our offset was greater than our limit, and it possibly went into partition 3, you would get a protection fault because that's not within partition 2. Okay. Okay, what is this? Process swapping. So process swapping, consider a case where a higher priority process arrives, but there's not enough space to load it, right? Where let's say partition 5 comes in and it's bigger than this block over here, and it really needs to get in because it's of higher priority. What do we choose? Like how do we go about that? The OS can simply have the higher process wait in the queue of processes waiting to be admitted to the system while until enough space becomes available. And then it would swap an entire process temporarily out of memory to a backing store, right? So you might get a question on the exam like, what is a backing store? This is what the answer would be. So we get put in the backing store and then bring it back later into memory for continue execution. Okay. And so a backing store is a fast disk large enough to accommodate copies of all memory images or processes for all users and must provide direct access to these memory images. Okay. So it's again just swapping one partition out for another because that one that's being swapped in, has a higher priority and needs to run. Okay. Now, there are some problems when doing variable partitioning with MMU and logical addresses, that problem being external fragmentation. So external fragmentation is when, let's say, this is what our main memory looks like right now. Let's say this block right here is 1 kilobyte, this block right here is 10 kilobytes, and this block right here is like 2 kilobytes. And let's say another process comes in, process 5, that is, let's say, 11 kilobytes. Now, our physical memory has more than 11 kilobytes of space free, but it doesn't have 11 kilobytes free of contiguous memory. It has just 11 kilobytes, over 11 kilobytes free, but this part is 1 kilobyte, this part is 10 kilobytes, and this part is 2 kilobytes, right? So there is enough room in physical memory, it's just that that room is not contiguous. This is known as external fragmentation, where you aren't able to load in a large process because there is not enough free contiguous memory in physical memory. So how can we combat this? We can use segmentation to combat this. What is segmentation? Well, in a process, you have 3 different parts. You have the code, you have the data, and you have the stack. Now, the code, data, and stack when you're loading a process into main memory, this is what the process consists of. But the code doesn't exactly relate to the data, and the data doesn't exactly relate to the stack, and the stack doesn't exactly relate to the code. And so what we can do is we can break the process into smaller parts. Okay. And when we break the process into smaller parts, that'll allow us to load the process into non-contiguous portions of our main memory, right? So let's say this is all the space we had left. We had P1. Let's say, just for this example, let's say the entirety of P1 is contiguous, the entirety of P2 is contiguous, and the entirety of P3 is contiguous, and we want to load in P4. We can break up P4 into code data stack and store its code here, its data here, and its stack here. Now, of course, the data memory must be contiguous, the code memory must be contiguous, and the stack memory must be contiguous, but these three parts of the process itself don't need to be contiguous, right? And so this is just I guess, a primitive solution to external fragmentation where it does help us a little bit, but it's not the ultimate solution, right? Oh, I also do want to say instead of one base and limit pair for each segment, so code data stack, each segment has its own base and limit registers, right? It has the base address of the data section and the limit register of the code section and so on. But anyways, so segmentation was still not the ultimate solution. And the modern technique is known as paging. Which paging is the main part of our exam. So paging, it solves external fragmentation by using fixed size units in both virtual and physical memory. What does this mean? Well, let's think of this as our main memory, so our RAM. Rather than just allocating space or allocating however much space a process needs in a RAM or in our RAM, we instead just divide our RAM into equally sized portions. Looks like this. They're all the same size. And then we load equally sized portions of memory for a process into this RAM. Right? And with this allows us to say, okay, this part of P1 I can put over here. This part of P1 I can put over here. This part of P1 I can put over here. P2 I could put over here. P2 I could put over here. This part of P1 I could put over here, and so on. This makes it so that, again, this is another solution to external fragmentation. So the pro is that you're going against external fragmentation, right? Where you're not just breaking up your process into three different portions like code data stack. Instead, you're breaking it up into n portions and being decided by your hardware specifications, and then you're loading it into RAM. Okay. And so here's kind of a visualization where this is our physical memory. It has frames and pages, which pages are just pieces of your program divided up into equally sized portions, and these portions are the same size, or the portions are less than or equal to in size than the frames, and each page correlates to one frame of physical memory. Right, so page 0 correlates to frame 2, page 1 correlates to frame X, page 2 to frame 0, page 3 to frame 1, and page Y to frame 3. Right, where it's saying, okay, this portion of my process is going to be loaded into frame 2, And this portion of my process, page 1, is going to be loaded in frame X. All right. What does this also mean for us? This also means that the entire process doesn't need to be loaded into physical memory. We can just load in what's required for us in our current execution state, right? So when a certain frame or portion of the process is not required, we can just schedule it out of the physical memory, right, and put it into our backing store or whatever you want to call it. I don't know if it's backing store still, but whatever. I think you would just store it in your disk. Actually, no, you would just store it in, I think it's a waiting queue in the kernel. I don't remember, but yeah. So this makes it so that the entire process doesn't need to be stored in physical memory all at once. Okay. And so how is this done? We use a data structure called a page table, right? We're in logical memory. Each page table or each process has its own page table. Okay. And a page number correlates to a index within that page table, and each value within the page table correlates to a frame number in main memory. So again, correlates to index 0 in page table, and the value at index 0 is number 1, which is frame 1. Okay. So any questions about this modern technique or anything we've gone over so far? Good. Okay. All right. So how do we do this address translation? Because we're no longer working with MMUs. We are now working with pages, and we're still using logical addresses. So how are we going from logical address to physical address? Well, wait, so paging is a form of segmentation? Basically, yeah, where segmentation just broke up a process into 3 parts, but now paging is breaking it up into n parts, where n is dependent on your hardware specifications. Segmentation is something different, but you can they're kind of similar, I guess you can say. Where segmentation, the process itself is getting split up, but then paging, the physical memory and the process itself is getting split up. Okay. So now with paging, our virtual address now has 2 different parts. We have the page number and we have the offset, right? Now the page number is an index into a page table. Like I said before, page number goes into the page table. And each page table entry, also known as PTE, contains frame number, where frame number is a address in physical memory. And so to find the physical address, you basically just take the frame number and you concatenate the offset to it. So for example, we're referencing this specific page number, let's say page number 2, and our offset is like 23 or something like that, then our frame number or our page number will grab the frame number, and then we'll have our frame number and concatenate 23 to the end. And then we'll use that to say, okay, this was where our frame number was, go 23 steps ahead. That's just a primitive example. That's obviously not how it works fully, but yeah. Okay. So page tables, again, are managed by the OS, and each process has its own page table. And this is just a little diagram. So you might be asked on your exam to draw a diagram. This is how it looks like. Okay. So here's an example. This is to find the physical address given a virtual address. So assume you are in a 32-bit architecture, and assume the page size is 4 kilobytes and the page number is 20 bits long, offset is 12 bits long. Okay. So only in this case where the page number is 20 bits long and the offset is 12 bits long, you can easily just do this. If you're in a different case where the page number is a different amount of bits long and the offset is a different amount of bits long, then it'll be different. But I'll show you those cases soon. Ackmar taught me it in office hours, and it's something that we can be asked on the exam. So in this case, we have this virtual address OX1332538. Notice the colors. The last three values of our virtual address is going to be our offset. So offset is OX328. And our page number is going to be everything to the left of the last three digits or characters. All right, so our page number is OX13325. Okay, and so we basically use this number, OX13325, to go into our page table and grab our frame number. So in this case here, we say assume the page table entry for this contains the value OX03004. Right? That's our frame number. So once we have our frame number, OX03004, okay, to get our physical address, again, we're just going to take our frame number and concatenate to the end the offset. And so our physical address in this case would be OX03004,328. Okay. So any questions about converting from virtual to physical? We take the last three digits for the offset because the offset is 12 bits long. Yes. But if the offset was like 13 bits long, you would still take the last three and you would like do some bit manipulation, which I'll talk about in a bit. Would there be any calculation on the final? What does that mean? Like something you need to calculate? Well, there would be the table, the translation, look aside buffer, estimation time stuff. Yeah, the memory access time. There's that. Okay. And so I want to quickly run through an example of what to do when your offset your offset and your page number is not correlating, meaning the page number is not 20 bits long and the offset is not 12 bits long. All right, so let me just grab my tablet. All right, and stop me if you have any questions because this is a bit confusing. So just let me know. Okay. So we're gonna go with this address here again. Right, where the last three is the offset. Oh, I'll just do like this. Okay. So the last three is the offset, and the rest of the characters in the front are the page number. So let's assume we're in a 32-bit address, okay? And let's assume that our page size is 8 kilobytes. So again, assume page size is 8 kilobytes. Well, to answer our question, we first need to see, okay, how many bytes is 8 kilobytes? Well, 1 kilobyte we know is 2 to the 10 bytes. I don't exactly have the answer why that is. Just know that, or it's just good to know that 1 kilobyte is 2 to the 10 bytes. but we have 8 kilobytes. We have 8 kilobytes. So we're going to multiply that by 8, but in that same notation. So 2 to the 3. Remember, 2 to the 3 is 8, because 2 times 2 times 2, that's 4 times 2, and 4 times 2 is 8. So you have 2 to the 3 times 2 to the 10. And when you're multiplying with exponents, you're just adding them together. So 3 plus 10 is 2 to the 13 bytes. Okay. From here, we need to say, okay, how long is our offset? How many bits is our offset? To do this, again, our page size is 2 to the 13 bytes. And so that's going to be represented by 13 bits, right? Take that exponent, it's represented by 13 bits. So our offset is 13 bits long. But remember, we're in a 32-bit system. So our page number, again, this is for a virtual address. Our virtual address is made up of the page number and the offset, D being the offset. Our page number, again, the pages themselves are 32 bits. So our offset already takes up 13 bits. So 32 minus 13, that's 19 bits. So you see in this case, page number is 19 and offset is 13. So we cannot do this, right? Where page number is just 20 and offset is just 12. We cannot go ahead and just say, okay, let's just do this concatenation stuff and call it a day, right? Because we require 20 bits when we have 19. Okay. And so for this example, again, this is our address OX13325328 and OX13325328. This represents our offset, and this represents our page number. But remember, the page number is supposed to be 19 bits and the offset is supposed to be 13 bits. But in this case here, each character in a hexadecimal is 4 bits. So 8, 2, and 3, we have 3 characters, each 4 bits long. So this offset is 12 bits. And then for this one, we have 1, 2, 3, 4, 5 characters. 5 times 4, that's 20 bits. So the address we're working with, the page number is 20 bits, and the offset is 12 bits, when the page number is supposed to be 19 bits, and the offset is supposed to be 13 bits. Okay? And so what do? We need to take a bit from our page number and give it to our offset, right? And so how do we do this? Well, we just need to convert this hexadecimal to binary, right? We're 1, 3, 3, 2, 5, 5, converted to binary. Again, each character is 4 bits. So 5 is going to be 4 and 1. So that's 1, 2, 4, 8. So this is correct, right? Then 2, that's just 0, 1, 0, 0. 3 is 1, 1, 0, 0. 3 is 1, 1, 0, 0. And 1 is 1, 0, 0, 0. This is 1. This is 3. This is 3. And this is 2. And this is 5. Okay. And at the end of it, we have that 328. So again, this is 20 bits, this is 12, but we need this to be 19 and this to be 13. So we're going to take the rightmost bit from the page number and put it into our offset. So it's going to look like this. Let's see if I could just grab it. I can't. Okay. We're going to take this one and put it over here. Where this is not a 1, again, it's a bit. That's our bit. And then we're going to take this new page number and binary that we have and convert it back to hexadecimal. So we're going to group by 4. This is 4, so this will give us 2. Group by 4. This will give us 9. Group by 4. This will give us 9. Group by another 4. This will also give us 9. And then this, I think, gives us 0. Okay. So this is our new page number, 09992. Okay. And so in a question like this, we'll be given the page table. In this question, we're not given the page table. It's just saying assume the page table entry contains this value. So I'm going to do the same thing. I'm going to say, okay, let's assume in this case that the page table at this page number contains this frame number right here. Right, so at 0x09992, we get the frame number 0x03004. Okay, so again, we cannot just simply go ahead and say, okay, I'm going to concatenate 1328 to the end of 0x3004. All right, because we still have this bit here. Okay, and so what we're going to do is we're going to convert both sides to binary. We're going to convert 03004 and 328 to binary, not including the 1, because again, that's already a bit. And so first, 328. 8 is 0001. 2 is 0100. 3 is 1100. And then the 1 is just the 1. That's 1 bit. And then for the 4, that's going to be 0010. The 0 is just 0000. The next 0 is just 0000. The 3 is 1100. And then the 0 is just 0000. Okay. So again, to get our physical address from here, we're going to convert this to hexadecimal by using groups of 4. So groups of 4 right here. This is 8. This is 2. This is 3. This is 9. This is 0. This is 0. This is 6. This is 0. And then how many are we supposed to have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And yeah, that's good. That's just an extra 0. And so this would be our physical address. Okay, I know that was a lot. But this is just what you would have to do if the page number is not 20 bits and the offset is not 12 bits. This is what you would have to do, right? Because our hexadecimal number for the page number, there should be 5 characters, each 4 bits. That's 20. And for the offset, there should be 3 characters, 4 bits each. That's 12. But if our offset or page number doesn't match that, then we need to do some bit manipulation for it to match. And so that's why we got a completely different answer than this. Here we had OX03004328, and now we have OX0600938. Okay? Yeah, he did not teach this, but he said that it will likely show up. That's the funny part. Okay. All right. So is everyone good with that now? Or do you have any questions on that before I move on? What's the leftmost zero mean? That is just an overcount. Like, remember how I had when we did it in class or in the library, Shamir? Where we had 1, but then I just left out the 3 zeros. Our final number is only supposed to have 8 digits, right? And so you can just consider that as like a trailing 0 because it should only have 8. If that was like a 1, then that would be a different story. Like, that we would need to deal with it. But it's not, so it's okay. Okay. Yeah, like if I wanted to, I could have just put a 0 here instead, and that would have been fine. But whatever. Yeah, you're welcome. All right. Any questions? Yeah. Oh, yeah. Also, remember this is hexadecimal, so just like Lauren put, A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay. All right. So moving on. We're going to talk about page table entries. I feel like he'll definitely ask one, just like list 3 items that are within a page table entry. So here are these items. We have the modify bits. Again, page table entry is what's actually inside the page table. It's not just the frame number. We have the modify bits, which says whether or not the page is dirty. And it is set when a write to the page has occurred. Right? The reference bit says whether the page has been accessed or is currently being accessed, and it is set when a page has been read or written to. And the valid bit says whether or not the PTE can be used, right? So says if a virtual address is valid and the corresponding page is present in physical memory. So if it's not valid or if it's not present in physical memory, then the valid bit would be set to 0. Okay, and it is checked each time a virtual address is used. If invalid, a page fault is generated. And then finally, the protection bits control which operations are allowed. So this is saying, okay, for this page, you're only able to read, or for this page, you're only allowed to read and write, or execute, and so on. Okay. And then finally, the frame number, we already know what the frame number is. It's just the base address of the frame number, or of the frame within physical memory. Okay. So again, you can get asked a question like list 3 things in the page table entry. I think the easiest to memorize would just be modify, reference, and frame number. The modify again just tells you if the page has been modified. The reference bit just tells you if it's been read or written to, and the frame number is just the frame it's just the base address of the frame within physical memory. Could we do another problem of the voodoo hexgate ship page numbers offset or whatever? Yeah, sure. Just not right now. I just want to finish this up and then we'll do that once we get to the practice problems. So some advantages of page table entries. It's easy to, or sorry, some advantages of paging, sorry. It's easy to allocate physical memory, right? Where physical memory is allocated from a free list of frames. And to allocate a frame, you just remove it from its free list. Okay. Also, external fragmentation is not a problem. It goes against external fragmentation, and it's easy to page out frames of the process. So all frames are the same size, so you can simply just use the valid bit to detect references to paged out pages, and page sizes are usually chosen to be convenient multiples of disk block sizes. But some disadvantages is you can still have an internal fragmentation. What is internal fragmentation? Well, let's say you have this process. Let's call it P1. And let's say our frame size is, let's say our frame size is 1 kilobyte. Okay. But our process 1, is 8.1 kilobytes. Then our process will be broken up into small 1 kilobyte pages. But on the last page, right, 1, 2, 3, 4, 5, 6, let me just make one more, 7, 8. On the last page, it's just going to store 0.1 kilobytes, right? Because it didn't have enough to fill up an entire page, but we still need to have that memory. And so when we load these pages into main memory, let's say this page points to this frame, this page points to this frame, but let's say the 0.1 kilobyte frame or page points to this frame, and it only uses 0.1 kilobytes of the 1 kilobyte memory space. And so this is internal fragmentation because you're saying you're wasting this memory, right? This is never going to be used because this frame size is being occupied by a 0.1 kilobyte page that does not allocate the entire frame. And so that's internal fragmentation. It's not like something that'll severely affect the process, but it's just wasting space. Okay. Then finally, you also have a memory reference overhead, where you have 2 references per address lookup. You have to go to the page table, and then you have to go to the memory. Whereas with physical address, you can just go straight from CPU to memory. Here you have to go to the page table first, and then the memory. And so the solution to this actually is to use a hardware cache to absorb page table lookups. And this is called the translation look-aside buffer, or TLB, which we'll get into in a bit. I think one final, is this one more? Yeah. One final disadvantage is that the memory required to hold page tables can be large, right? Where In an example, you need one page table entry per page in virtual address space. And let's say you have a 32-bit address space with 4 kilobyte pages. You'll need 2 to the 20 page table entries, which is 1,048,576 page table entries, which is quite a bit. Okay. And that's going to be 4 megabytes per table. And so the solution to this would be to page the page tables, which that is 2-level and multi-level page tables, which we'll get into in a bit. Okay. So we're able to make page tables a bit more manageable. An example is a size of a page table for a 32-bit address space with 4 kilobyte pages. It was 4 megabytes, which we set up here, which is a bit too much overhead. And so the way we can reduce this is that we only need to map the portion of the address space that is actually being used, but that's a tiny fraction of the address space where, let's say our page table entry is this big, but we're only using these pages right now. All right, so you only need page table entries for those portions. And so how can we do this? We make the page table structure dynamically extensible, meaning you can have our page table point to other page tables that are able to be extended. And so that brings up 2-level page tables. Or with 2-level page tables, the virtual addresses now have 3 parts. This is our virtual address here. Instead of just having a page number and an offset, now you have a master page number, a secondary page number, which this is P2. Don't confuse it with P2 as in process 1 and process 2. This is our master page number, this is our secondary page number, and this is our offset. And so how it works is that the master page table maps master page number to secondary page table. So P1 indexes the outer page table, and the outer page table gives us P2, or page table 2. And then P2, or the secondary page number, maps the secondary page number to page frame number, right? So P2, this would be P2 here, and that would give us our frame. So this would be our frame, and then you would use our offset. Okay. And these inner page tables, they're now extensible, so you're able to just add page table entries for currently active pages to the page tables, rather than just having one single page table with every single page entry for our process, even though we're not using those pages. Okay. Here's a little bit of an example. We don't really have to go through this, I don't think. 12 bits. Yeah, that's pretty much what we did. Talked about the page offset. It says how we get the offset to be 12 bits. And so the remainder is 20 bits. And so that's split between the 2 page tables. Inner page table must fit into single frame. And 1 frame is 4 kilobytes. That's okay, yeah, whatever. Give me 1 second. Okay. Okay. So when we're working with multi-level page tables, it becomes a little bit inefficient because of the amount of page tables, right? Where with 1-level page tables, this scheme, 1-level page table scheme double the cost of memory lookups, right? But 2-level page tables triple the cost, because now you have one page table you need to look at, then another one, and then the memory. So that's 3, right? And with 1-level page table, that's just the page table and then the memory, so that's 2. So you're tripling the cost with 2-level page tables. And how can we improve this? Well, we can improve this using a hardware cache inside the CPU to cache the virtual to physical translation in the hardware. All right. And this is done using a translation look-aside buffer. Okay. And so the TLB is managed by the memory management unit. And how it works is that before checking the page table, we see, okay, is what we're looking for already in the cache? If it is, just use that, and then we can skip through all of the page table levels and stuff. But if it's not, then we have to actually go into the page table. So the translation look-aside buffer is a fully associative cache, meaning all entries are searched in parallel. And it translates virtual page numbers into page table entries. Wait, with PTE plus offset, maybe you can directly calculate the physical address. Yeah. Okay. So it's able to grab the PTE, and you already have the offset. And so since you have this, the memory management unit can directly calculate the physical address without having to go through all the page tables. But if it's not in the cache, again, so when a TLB miss occurs, the MMU walks the page tables to load the required page table entry into the TLB. And if the TLB is full, a victim page table entry is evicted based on the TLB replacement policy, which is implemented in the hardware. A little note on context switches with TLBs. During a process context switch, the OS switches from one process to another. And so when this happens, you don't want processes from process 1 to be in the cache while process 2 is running. And so to avoid stale translations, the OS flushes the TLB, which invalidates all the entries. And this forces the new process to repopulate the TLB from scratch, causing TLB misses and slowing down memory access. And so there is a way to go around this by adding context IDs to your page table entries within the caches, where you can say, okay, this page table entry belongs to process 1, this page table entry belongs to process 2, and this one belongs to process 3, so that when we do have a context switch and we go from, let's say, process 2 to process 3 will just ignore all of the page table entries within the cache that don't belong to its context ID. Okay, so it's going to ignore the ones that are for process 2 and process 1, and it'll just work with the ones that are for process 3. Okay. And so with our new memory access time saving mechanism, we now are able to calculate our effective memory access time. Okay. Sorry, give me 1 second. Okay. Where our effective, I'll do n level page tables. So how can we calculate the effective access time for n level page tables? We're going to be working with several different variables. We have our associative lookup, which is represented by this epsilon. We have our memory cycle time, which is beta, and our hit ratio. In the question that you get, like find the effective memory access time for this, it'll be like for epsilon, it'll be the TLB access time is this, so that'll be the value of epsilon, and the memory access time is this, so that'll be the value for beta. And then the hit ratio is the percentage of times that a page number is found in the associative registers. What does that mean? That means that the percentage of times that there's a hit on the TLB. And that's represented by this alpha. And so this is the formula where you have beta plus epsilon times your hit ratio. What does that mean? That is the memory access time plus the TLB access time times the hit ratio plus, and I edited the formula here a bit, n1 plus beta, where n is the number of levels. So let's say on a 5-level page table, n would be equal to 5, plus 1, so 6, times beta, plus e. for beta, again, is the memory access time, and epsilon is the translation look-aside buffer access time. And that's going to be multiplied by 1 minus a, which is the miss. So this is the miss, and this is the hit. Okay. All right, so that's pretty much it for TLB. Any questions about that before I move on to page replacement algorithms? I think that's the last topic here. Yeah, it is. Any questions on what I talked about up until now? No questions? All right. So now we're going to go on to our page replacement algorithms. These page replacement algorithms are like when you have a certain page in main memory and you want to swap it out with another page of higher priority or something like that, you would use a page replacement algorithm. There's 3 types of page replacement algorithms. There's Bilouti's, there is FIFO, and there is least recently used. So for Bilouti's, this is a hypothetical algorithm that's used to compare other algorithms. And what it does is it basically looks into the future and it picks the page that won't be used for the longest time, right? And again, it's used as a measurement to compare other algorithms. So here's an example. Here's our reference string of pages that are supposed to be coming into main memory. And these are our page frames. Okay. Now, at this point here, when the 7's coming in, no frames are full. So we put in 7 and we get a miss. Here for 0, we get a miss. And here for 1, we get a miss. But for 2, we have to say, okay, our frames are full and my 2 isn't in it, so it's a miss. What do I replace it with? Well, for Bilouti's, we're saying we're going to replace it with the one that isn't used for the longest time in the future, right? So from this 2, we see the 0 gets used, so this one isn't the longest time. And we continue forward, we see the 1 is used, so it can't be the 1. And if we continue, we see the 7 gets used for the first time all the way over here. And so we're going to replace that 7 with a 2. Okay, let's go through one more before we move on to the next algorithm. We see with this 3 is not in here. We have 2, 0, 1. So I'm going to put a miss. We say, okay, what do we replace the 3 with? Well, 0 appears right here, so it's not the longest time. 2 appears right here, so it's not the longest time. And 1 appears all the way over here. So 1 would be the longest time. And so we're going to replace with 1. Or we're going to place the 1 with a 3. Okay. Agricultural habit said TLB, and why does it make memory access? Oh yeah, someone responded. Okay. Okay. So this is just Bilouti's algorithm. Any questions about this? Before I move on to FIFO, all good? Okay. So FIFO, it's what we've been working with since like 211 and 212. Just first in, first out. Pretty simple. You basically just have a queue and you remove what's at the front. So in this example here, the frame is initially empty. And we say, okay, is 7 in it? No. Is 0 in it? No. And 1 is in it? No. But there's free frames, so we just load them in. But at 2, we say, okay, there is no room, and we have a FIFO replacement algorithm, so let's remove the first one that came out of the ones that are already in it, and let's load myself in. So which one came first? 7. So we're going to replace the 7 with a 2. And for the 0, we get a hit, And then for this 3, we say, okay, it's a miss. What do we replace it with? Well, we have a 0, a 1, and a 2. The 0 came first, so we replace the 0 with a 3. And then finally, in the 0, we get a miss. So we're going to say, okay, which one do we replace it with? The ones that we have right now are 2, 3, and 1. How it was is it was 1, 2, 3. So 1 came first, so we're going to replace the 1 with a 0. Okay. All right. And so with FIFO, there's actually a anomaly that it suffers from called Bilotti's anomaly. There might be a question on the exam that says like define Bilotti's anomaly, so this is good to know. It says the fault rate might increase when algorithm is given more physical memory, right? Where you would expect Bilotti's anomaly is that you would expect the hit rate to decrease, or sorry, you would expect the fault rate or the miss rate to decrease um, if you were to increase the number of frames. But Bilotti's anomaly shows that for an algorithm like FIFO or FIFO, whatever you want to call it, if you increase the number of frames, there's a chance that the fault rate might actually increase, given a certain reference string. Okay. All right. And then finally, least recently used. So the final one is least recently used, LRU, and pretty straightforward. It replaces the one that's least recently used. So this example here, I'm gonna just try to fast forward on this 3. Currently, the frames contain 2, 0, and 1, but a 3 comes in and says, okay, I want to start. What's going to happen is it's going to say, okay, what do we want to replace with? The 2, the 0, or the 1? Well, which one was least recently used? The 0 was used over here, the 2 was used over here, and the 1 was used over here. And time progresses this way. So 1 was least recently used, so we replaced the 1 with a 3. Okay? Okay, so that's pretty much it for the topics, or the main topics for this part. Now I think, yeah, we just go into practice problems. So what we're gonna do actually is, yeah, we have quite a bit. Let's take a break before we're going to the questions. It's already 10 and we started at like 7:30. Let's take a 30-minute break. You guys can feel free to look over your notes or go over the problems yourself and then get ready to compare your answers. We'll be back at 10:30. What's up, Shane? No, I'm not playing League during the break. Okay, I'll be back at 10:30. You guys can feel free to just sit in the chat. Oh, is the algorithm the same as the one Vivek taught us before? Yeah, it's the same. Yeah, I'll be back at 10:30. So feel free to just go relax for a little bit, or do whatever you're gonna do. But I'll be back at 10:30.